Sound waves. Sound waves are mechanical waves that travel through a medium such as air, water, or solids as vibrations. These vibrations propagate as compressions and rarefactions, causing particles in the medium to oscillate back and forth. Key characteristics of sound waves include frequency. The frequency of a sound wave refers to the number of complete cycles of compression and rarefaction that occur per second and is measured in hertz, AODs. Wavelength. The wavelength of a sound wave is the distance between two consecutive compressions or rarefactions. Amplitude. The amplitude of a sound wave represents the intensity or loudness of the sound and is related to the magnitude of the oscillations in the medium. The Doppler effect. The Doppler effect is a phenomenon observed when there is relative motion between a source of waves and an observer. It causes a shift in the frequency and wavelength of the waves perceived by the observer compared to the frequency emitted by the source. Mechanism of the Doppler effect. Moving source. If the source of waves is moving towards the observer, the perceived frequency of the waves increases, resulting in a higher pitch. Conversely, if the source is moving away from the observer, the perceived frequency decreases, resulting in a lower pitch. Moving observer. If the observer is moving towards the source, the perceived frequency increases, leading to a higher pitch. If the observer is moving away from the source, the perceived frequency decreases, resulting in a lower pitch. Applications of the Doppler effect. Astronomy, redshift and blueshift. In astronomy, the Doppler effect is used to measure the motion of celestial objects such as stars and galaxies. A redshift occurs when an object is moving away from Earth, causing its light to shift towards longer wavelengths. Conversely, a blueshift occurs when an object is moving towards Earth, causing its light to shift towards shorter wavelengths. Meteorology, weather radar. Doppler weather radar systems use the Doppler effect to detect precipitation and measure wind speed and direction in the atmosphere. By analyzing the frequency shift of radar signals reflected off raindrops or other atmospheric particles, meteorologists can determine the velocity of the precipitation and the presence of wind patterns. Everyday life. Traffic radar. Police officers use Doppler radar technology to measure the speed of vehicles on roads. The radar emits microwaves towards moving vehicles, and the frequency shift of the reflected waves is used to calculate the speed of the vehicles. Medical imaging. Doppler ultrasound is a medical imaging technique used to visualize blood flow in the body. By measuring the frequency shift of ultrasound waves reflected off moving blood cells, doctors can assess blood circulation and detect abnormalities such as blockages or narrowing of blood vessels. Conclusion. The Doppler effect is a fundamental principle that influences the perception of sound waves and has numerous practical applications in various scientific and everyday contexts. By understanding how the relative motion between a source and an observer affects the frequency of waves, we can interpret and utilize this phenomenon in fields ranging from astronomy and meteorology to traffic monitoring and medical diagnostics. Thank you for watching. Please subscribe for more.